Hi. Is it okay? I think it's okay now. I'm sorry.
Yeah, it's okay now.
Okay. I'm sorry. So I take 1 or 2 minutes to briefly go over what we're doing.
I've asked
So in short, we talk about the course outline. Basically, what I'm trying to say is what is written, and so good luck. And anything special? Because basically, the assignment we were trying to do is ask you to do some group presentation, and the project will be just same as last year. I don't know what to say. I mean, you have a particular question because I don't go over what we have covered. Is that okay? So just very briefly. So basically, we cover 3 parts. Yeah. Basic part is the individual decision making, and the game fit interactive, and this advanced. And I just try to say we are able to cover A and B, C will be problematic. I try to do it because we skip some classes, so probably I would just put it in the makeup class. We cover that, try to cover. And the textbook. I mean, but this is important. Maybe this is the book that we'll be trying to follow. And the Rubinstein with the textbook that if you are confused with the Jetil and Rennie, then Rubinstein will be a good one. For passing our class or whatever, the lecture slides would be sufficient for all purpose. In case you don't understand, you can consult the books. Okay, of course you can talk to me. I think we have actually I forgot to mention our TA is over at the rear corner, trying to help us. If any case, you can just ask him, and if you can not help you, then it will be me. I mean, of course, PhD student, I guess you can try to look for me. I mean, whenever you have time. Of course, this semester I'm super busy. Means I'm teaching a lot, so basically I'll be here every day. Sometimes Saturday and Sunday. So probably you're able to easier if you want to make an appointment. Probably Saturday and Sunday will be easier. But I'll try to. If not, then maybe Zoom will be okay. Okay. If you have any big question, but I guess for our class shouldn't be too big, because it's all a standard thing. Okay. There's not something I just try to teach my own paper that would be difficult. Right. It's not the frontier of research that have been there for like 30 to 40 years. So there's nothing very special, right? And also, I think the past 2 years lecture has been uploaded. You can look at the YouTube and try to see stuff. Okay. I mean, as I said, the difference about this year, the last year will be less technical. So this year probably is a subset of last year, so shouldn't be an issue. Okay. So we are going for the slide. I mean, make sure that you are. Can you see the slide for Thai?
Yeah, I can hear. I can see. Yeah.
Sorry, I to make sure that if you can't see, then you just please leave a message, because when I full screen, I really can't see it. So any question before we actually, maybe I don't need both mics. I just take out one. Okay. So for this one, we just cover consumer, very standard thing. That is basically the main thing about microeconomics, right? Human, right? Is the consumer, and that is the things that we do it every day, right? We consume to survive. We make choice, right? So basically, consumer theory, people usually call it a choice theory of your choice, right? We make decision every day, right? I would like to refer student to watch Matrix, the movie, which the happening is the main thing about the movie is the choice, right? It's making a choice between saving his loved woman and the world, and he tried to save both. Of course, he win, but anyway, in the real world, then we have to make choice. That is actually the main thing you learn from your first class of microeconomics. Economics is about opportunity cost, right? The trade-off. The things you choose then you give up, right? Something else. So, and by modeling how consumer make choice, which is the common thing you do, you learn how human make decision. And the one main thing about this consumer is we have limited budget, right? So we're doing a choice under constraint, which is different from the next chapter we're doing the firm, which usually model as choice without constraint, right? We maximize profit and we can utilize whatever we want to. Okay. And that is the different way to do it. So that's why this is more difficult than the next chapter. And we start from the more difficult one first, and then we'll do the easier one later. Okay. And what is different from your intermediate class is what we're trying to do is we have the what we call the starting from preference. I guess what you learn from intermediate, you learn the indifference curve, right, and find the bundle, so on and so forth, right? The only difference is we start from utility. Sorry, we start from preference. Where like the mathematics is starting from foundation, we make some assumption of how people make choices, and these choices will go into utility. And how people make preference is we make by assumption what we think that it should be correct, okay? And that means that a lot of marketing research, a lot of behavioral economics research is go beyond this point. And usually they would use more elaborate thing, what should be the right way human think, or what actually human do, okay? That will be adjusted by more elaborate assumption, justified by experimental result, right? For example, you know, a lot of many of us will fall into sunk cost fallacy, right? Because we invest so much, we don't want to give up, right? That's what happened when you watch TV movie, right? The guy or girl try to break up, right? The girl is crying and asks why, and then, oh, I have with him for many years, I don't want to break up, right? But if you don't fall into the sunk cost, right? What sunk cost is what bygone is bygone, right? If you continue, right, look at what happened in the future, not in the past, right? No matter how many years with him, doesn't really matter anyway, right? So that's look at forward-looking rather than backward-looking, right? But all of us would fall into that anyway, right? That's why we watch that movie, TV, so all the time, right? So that would be the first part. The second part, probably you would have learned it from the maximization problem. Probably you would have learned it in the intermediate class. So I'll try to be quick. What we're trying to do is to give you the formal way, how actually from preference to utility maximization problem, and highlight some of the interpretation. And the cost maximization problem will be the other way to look at the same thing. If you learn linear programming, that will what we call the duality, right? The maximization problem and the maximization problem, this is the flip side. And probably you ask why with the two problem for the same thing. The reason is being that when you do empirical, or the assumption is different. Okay, because if you do utility maximization, you have to know the utility, right? That will be much more difficult. You make a lot of assumption there, which have to be tested. But when you do cost minimization, actually you see the assumption we're making is much less. Okay, and so that's why people actually, when you do empirics, they will start with indirect utility or exponential function, right? Because you never observe, very difficult to observe demand. Of course, we estimate demand using regression, as many of you do in the marketing. But that is something we try to do. And for another reason is when you do these two, and then you learn the same technique when you do the firm in the next class. Okay, so that is the reason why you see the symmetry there. Okay, and the last one is called consumer surplus, which try to give you for the foundation why this is a good measure of consumer welfare. And probably many of you will not care consumer surplus, but if you do policy or you do anti-trust competition, or antitrust authority, that would be the things that they care. So I will just briefly talk about consumer surplus, but that would be just give you the application of what we have done. So the main thing is give you the foundation for the utility, okay? Because the rest probably you have learned already, right? So just give you a more robust way to do stuff. Is that okay? So I forgot to mention my usual class arrangement. We will be 45 minutes, 15 minutes break, 45 minutes, 15 minute break. Okay. Because I can continue talk 3 hours, but I don't think you can take it. I mean, when I student, I always long for a break. So I try to make sure that I keep the break at 15 minutes long. Okay. So preference. So we start from the assumption, okay? So this is very standard. We started from commodity space. So we try to represent what we consume by a number, okay? And the number we consider finite types of commodity, okay? And you represent it by a vector of numbers, usually a real number, right? And positive real number. And each commodity is infinitely divisible, okay? So this is standard thing we are using. Of course, there are a lot of issues here, okay? When we talk about, okay, going to do your Ph.D., right? Either you have 1 Ph.D. or no Ph.D., right? Or maybe 2 even, but you don't have 1.5 Ph.D., right? You don't have negative Ph.D., okay? Even you are unfortunately kicked out of the program, which never be the case, but it happened if there's no negative Ph.D., right? And so that would be something that, especially the infinite divisible is a problem, right? For many applications, right? Because people either buy or no buy, right? Or as a firm, you would try to restrict the choice set, right? Like bundling, right? Say, suppose you are going to have an iPhone, right? And you have a phone, then you try to subscribe the mobile service, right? Either you have monthly or nothing, right? Or even if you pay card, right? It's just like you have to buy lump sum, right? So basically the firm will try to limit what you're doing, right? So the feasible set need not be continuous. And why I want to mention this technical thing? Because actually this kind of discontinuity or indivisibility is important when you do some research. Okay, so do note that this continuity not innocuous, but a lot of things can be different. Okay, so that have to be, and as a firm, you can use indivisibility to make more profit. Right? There's a way that you is not make it to not continuous. Right? So, and this is what I mentioned, right? So you represent your consumption bundle, or as a vector of numbers. To reiterate, is a vector of non-negative numbers. Okay, and as I said, there's a lot of restriction on this as well. So everything looks natural, but a lot of restriction, and research is basically trying to attack these kind of loopholes, right? Whether you make this assumption, you're missing something or not. Okay, even from the very beginning, commodity is a vector of number is already an issue there. Okay, right? Because when you learn physics, right? Some of you may have learned that the world should be represented by complex number, right? And actually, that people don't research saying that you should use complex number to present the commodity. But anyway, we are the more rational people, so we just follow the very standard thing. So this example here is a very simple 1, 2, 3. It means that we have 3 commodity. We consume 1 unit of 1, 2 unit of 2, and 3 unit of 3. So that's a very standard stuff. Okay. And here we will present our consumption set, which is something feasible consume by a capital X, which is a subset of the n-dimensional Euclidean space of positive non-negative numbers. And actually, this is also very useful when this is the constraint is imposed by the firm, right? Because for a firm, usually we impose a constraint what you can consume, we just mentioned now, right? And but in our presentation, we'll just focus on the whole possible number space. We don't put any restriction, okay? And when you apply to your work, probably you want to impose restriction, or the firm actually put restriction, right? A lot of things that actually this doesn't hold in a standard way is like your is geography constraint, right? Geography constraint, right? Either you are in Sa Tien, Hong Kong, right? So you can't be Macau, you can't be in Beijing, you can't be in Taiwan, you can't be in US, right? So this geographical constraint is limit, right? Or attention, or many other things actually with psychological with limit anyway. These are the things that are actually would go into your decisions, where you're aware or not. Okay. So is that okay? So we start with a consumption set, which is represented by vector of positive, also non-negative numbers. Okay. So this is a very standard, although very natural, but you would be something you do, right? Actually, when I try to draw a graph, right? Usually when you learn intermediate, right? Your graph, a two-dimensional thing, already you make the assumption, right? Whether you're aware or not, but that is the something we first we make that's a positive or non-negative number, and then you can represent by number, right? That is something that you have to be aware. Now, probably I will do the binary relation and we'll break. Okay. So this is a math thing. I'm sorry I do the math thing because if I don't talk about math, then you can't read those textbooks because they are written in the way that if you don't know the terminology, that you can't read it. Okay? So we try to introduce a concept of binary relation. Is it learned in the math camp or not? Did you learn this math camp? Okay, you learned that, right? Okay, so binary relation will be just it's a subset of the product space, right? So you try to say how two elements in the set are related is actually the element of product set, right? So usually a binary relation, a triangle of X, okay, square, it just, if this is inside, it will be there. Okay, maybe where's the pen? Yes, maybe this is good to draw a graph. Oh. Although I know it's very trivial, but I want to oh, it's not drawing. Is it drawing? I know. Oh, okay, the screen is not working. Then I use my hand. So this is x1, this x2, right? A binary relation is how any elements are related, right? So if I have this is called bundle X, okay, and this is bundle Y, right? If say we use the concept called beta, right? If X is better than Y, right? Or X is related to Y in the triangle way, right? Then this XY will be in the set. Okay, so the usual binary relation is like, is it the one that let's see the example will be more clear. So the example will be, say, we used a simple set is just a single number, right? A equal is a binary relation, right? Because what is that there is actually the 45-degree line. Okay, so all these lines in the set, right? Because they're equal. All outside not in the set, they're not equal, right? And this width inequality, right? The binary relation is like this. So this is the set called equal set, right? And this width inequality, right, will be the set like this, right? Because everything here, the x coordinate is better than y coordinate, right? And for the strict inequality, then will be same, but without that line. Is that clear? What do you mean by binary relation? That is it, just by definition. Okay. It happened to me that I spent like 1 to 3 months to understand what actually it is, but I thought it was very simple. But I spent a lot of time thinking about what's binary relation. But actually, it's a very simple thing, right? Nothing, but just a way to describe how they're related. So why we care about binary relation? Because this is our starting point, is our defined preference. Okay, our preference is try to compare binary comparison. Okay, is compare, give me 2 vector or 2 bundles. We are trying to tell which one you like better, right? Or at least as good as. Okay, so the assumption we make for consumer, which we call rational later, is the preference is complete. Okay, so you can either say X better than Y or Y better than X or both. When they're both, that means equal, right? So you can interpret this binary relation is called the at least as good as, right? Or no worse than, right? X is no worse than Y, or Y no worse than X, right? So this is called complete, means that you can always tell. Okay, you can always tell which one is better. You can't say I can't tell. Okay, or you can't say it depends. Sometimes X is better, sometimes Y is better. Okay, what does that mean? It means that we have a complete picture of what we're going on. Okay, if it depends, it means that the vector we have is not complete, right? We don't have a good description world, right? Because later when we learn, if it depends, then we would actually have to write a bundle in a way that if this happened, you have this. If this happened with that, we call the state of the world description. In that case, you have a complete description, then you can compare, right? Suppose the following, right? And one question is, a big example would be, okay, a common dialogue will be, a guy asks the girl, we say, do you like me? The girl says, it depends, right? It depends on what, right? It depends on whether the boy have a house or have a kuko, right? Or have a lot of money, right? It means that if money, then like him, no money, not like him. Okay. Then it should be the reason why the girl cannot say, because he don't know whether the boy like him or not, right? The boy is rich or not, right? In that case, if he know, then he can look at the whole bundle, then he can make a decision. So the question saying it depends or I can't tell, it means that we don't have a good description of the whole thing. And in the assumption about capital X is, in this current one, is the decision maker has no everything. It has to say yes or no. Okay, so cannot say I don't know, or it depends on tomorrow's weather. Okay, it has to be like this. Okay, and one example we have is completeness, right? And try to tell you that the completeness is very strong, it's not weak, because, like, for example, an example in the math is like the equal, it's not complete, right? Because you cannot say about if 2, 1 is not in the equal and 1, 2 is not equal. Okay, it's not there. And as I said, in this model, the decision maker know actually everything. There's no uncertainty, right? So there's a big assumption there, right? Because you know everything, then you can make decision, right? But often the time we do not know, then we have uncertainty that we cover in the 4th class. But that would be the idea, right? So you have to know what's going on in order for this to be true. Okay, so the completeness is an important, and and I can tell you experience. Actually, I think a few days ago I met a friend, and his daughter is like 5 years old, and you try to ask her, I mean, whether she like her father or mother or her grandfather, grandmother again, and then he can be able to rank consistently and a complete preference. Ask whether you like your dad or your mom, then she can take that more, right? And then so on and so forth. Okay, you able to tell. If you say, okay, on Monday is father and Tuesday is mother, first is grandma, then it's not, right? I mean, it depends on the day, then it's not. Or unless you say your preference include those kind of things, right? If you want to incorporate that, it have to be, the bundle have to be describing every day's preference. Okay, so the description of this, you can see when I try to incorporate the state of the world, it becomes problematic. One thing quickly is because of we assume the capital X is finite, right? When you think about the state of the world and those sort of things, the thing become infinite. So things can be problematic. Okay, but we are not worried about the technicality here. Okay, and sorry, I overrun a little bit, but let me finish this guy because I think that would be finish the whole part. I'll give you the 15 minutes break for sure. No, don't worry. Just 2 more minutes. Okay. So the last one we have is called transitivity. The reason why I have to finish this one is because when people said people are rational, or rational preference means 2 things. One is complete. You can give you 2 bundles, you can compare. You can always say this one is better. Okay. And the second one is transitivity. Because why we need that? Because remember, what we are asking for complete preference is we are able to compare 2 vectors or 2 bundles, right? And usually we are not given 2 bundles, we're given a huge set, right? A, B, and C, right? Even you choose, right? And even 5 or 6, right? And how can you extend from comparison of 2, pairwise comparison, to a choice in a set, right? So the way to do it is called transitivity, right? If you know how to do 2-way comparison, if you want it to be consistent, okay, then the transitivity will extend what you pairwise comparison to the choosing a set, right? Because what he said is if you prefer X to Y and Y to Z, then you can do X to Z. Okay, then it means that if you don't do this, then the thing will be very difficult, right? Because it depends on what kind of thing you present, right? If I present you X and Y, you choose X, Y and Z, you choose Y, and X and Z, you choose Z, then it really depends on how the thing is being presented, right? So here is, it doesn't really matter how you present, how you present it for the thing, right? You would always consistently, you will not run into weird concept. But I'm assure you that this is also very strong, and we often violate this one. Okay, this relation often violate, and of course, if people are aware of it, usually they don't fall in the trap of this. But if you're not aware, that's very often. And in transitivity is very often violate because we have what we call the limitation of our cognitive ability, right? Say, for example, this is a very interesting thing, what we call the paradox in the logic, right? Say, suppose it's a very common example is I try to take out 1 hair from your head, okay? Probably, maybe I pay you $100, probably don't mind, right? For exchange for $100 for 1 of your hair. Maybe if you don't enough, give you 1,000, right? And if I keep doing this, right, probably at some point you will not be happy with that, right? Because you end up with no hair. Why? Because of the continuity argument, right? Because take out 1 hair, we fine, but you keep doing things, then will be different, right? So that means that your preference is like somewhere in the middle, or somewhere nearby. You don't think a difference. But if you move a lot, there will be a big difference. Okay, say for example, you've often used it in marketing, right? Things put $1.99 is people psychology will be different, right? And that often been used. And just like also like color, right? I don't know you have experience. I mean, some of you maybe are coming your wife, your girlfriend to the boutique shop, right? And they have many colors, right? And of course, black and white is very different, right? And black and slightly little bit less black and slightly black will be, I mean, you can't tell, right? But when you try to move at the spectrum, then it will be very different, right? And probably can't tell, but your girlfriend or wife will be tell, right? But because they ask you to buy a X color, and then you buy slightly off, then will be way off the chart, right? So that would be the color thing is like same thing, right? Because something very similar, but if you go further, then will not be the same. So maybe I take a break of 15 minutes. In the meantime, if you want to leave the room, then feel free to do it. I will resume in 15 minutes later. So let's resume at 10:38. I guess we can resume. I mean, the break is always too short for whatever reason. So the thing we cover in the first 45 minutes was we described the choice that faced by the consumer is a Euclidean space, okay? And basically it's a positive vector. And we assume the consumer is able to tell which two vector or which two bundle is better, right? And the pairwise comparison is consistent in the sense that if X better than Y, Y better than X, then you'll be X better than Z. So we will not going into a cycle, okay? And some of you actually mentioned this, right? It's a partial order structure there, right? But I don't want to do mathematics, but some of you may have remember from the math class, that would be something we do. And this example, equal sign is transitive, right? And same as with inequality and strict inequality, they are all transitive, okay? So most of the thing we think is a normal, is transitive, right? But remember, complete is not there, right? Because as I said, the equal thing is not complete. Okay? So complete and transitive is defined as what we said is we call it a preference or rational preference. Okay, so just to remind, when we say preference, we already assume two things: a complete and transitive binary relation. Okay, remember we talk about binary relation. We are talking about comparing three bundles. Okay, we just compare two every time. Okay, and we actually assume our mind is able to compute or choose the best one out of no matter how many choices we're given, right? Suppose we give you 10 choices, you're able to pick the one. I give you 1,000, you're still able to do it, okay? And that is very strong, okay? And many of us are unable to do it, right? That's a very famous thing, right? I don't know, many of you may not drink wine, but if you're given a wine, the famous thing is you would choose the second to last expensive wine because you don't want to be look cheap and then you don't want to go too cheap. So that's the thing, right? So that means that you would actually depends on how your choice being presented to you, but this assumption assume you don't have this problem, right? So we can always compare and that's consistent, okay? And the next is indifference. That is very simple. If X prefer to Y, Y prefer to X, and indifference. And why I talk about this? This is because you learned that in the intermediate class, we call indifference curve, right? We actually don't start with the preference. We start with indifference curve in the intermediate, right? When you are principal class, we start with downward sloping demand. That's the starting point, right? For the intermediate, you start with indifference curve, you give you demand. Now we advance, we start with preference, and indifference curve, and then downward sloping demand. So that is the goal. Okay. So do look at indifference curve, right? Same as equal, so that satisfies transitivity but not completeness, right? Because that is same as the equal thing. And very often we have called the strict preference. That is strictly better. Okay, that means that this is at least as good as, but not true the other way around. Okay, and again, it satisfies transitivity, not completeness, but that is exactly similar to the strict inequality in math, right? So that is nothing more special here. So this is the name that usually given, but I'm not going to cover it because it's name. I don't see the reason why I want to go one by one. You can check it out. These the name are copied from Jathu and Rennie, so you can, if you have any issue, let's go for it. Okay. So one thing I want to highlight is you try to look at the Rubinstein book I mentioned. he did not start with the binary relation. Okay. Instead, he tried to start with the trinary relation like this. He would consider one of the following must be true. Either X is strongly preferred to Y, or Y strongly preferred to X, or indifference. Okay. And this is the same way as we do the binary relation. Okay. But he thinks, which I agree, this is more natural way to start than the way we did, right? Because we start with binary and then we do this way, but I think it's more natural to think from this angle, but they're equivalent anyway. So whether you like yourself to start with this weak preference, right? And assuming transitivity and completeness, or you start with this, okay, assuming there are transitivity, right? Goes on, be the same. Okay. Actually, in his book, he will tell you they are the equivalent thing. Okay. Of course, there are many ways to start with the preference. Then which way is more natural? Depend on your taste. Of course, depend on experiment result, but they're the same. Okay. Now we have the preference. So what we want to do from now on is from preference to utility. What assumption we need to make to derive utility, okay, function. And the question would be, what kind of property of utility function, when we assume we work our model, what actually assumption we are making for our preference? So that's important part. Let me repeat this statement, okay? We, in applied work, we never start with preference, right? We always start with utility directly. So the question why I want to make here, what to learn here is, we want to learn when we make assumption on the utility, actually what kind of preference we're assuming, right? Because then we will be saying that this is reasonable or not, right? Because we always start with utility when applied work, right? We never start with preference. So we'll try to understand how they're related. That is the goal. Okay. And because the goal of preference is we can test it in the lab or test it from the experiment, right? That is the goal. Okay. And now we start with the idea we call the open ball. I guess everyone knows it with the math camp. And so give you two points in the Euclidean space, and the Euclidean distance is just the each dimension distance square and take the square root. So there's nothing new there. It's Pythagoras theorem. And the main thing we define, we call open ball, right? The open ball is just at X will be an open set, okay, with positive radius R. That's and circle it. You can, in your mind, just we call this just a neighborhood, right? Neighborhood is nearby. Anything next to it. Okay. We need this because later all the definition require us to refer to open ball. Okay. Is that okay for this one? I guess most of you are math oriented, better math than I do, so it doesn't really matter anyway. Okay. So the first assumption we have is called no colon satiation. It essentially means, without looking at math, it just say pick any bundle, okay? And you can always find a better bundle in the neighborhood, okay? Basically, I can take away something from you or give you something, okay? Always you would think that one is strictly better, okay? As I said, this assume actually the space is continuous, right? It's a compact set. I mean, otherwise, if have to be indivisible, that thing would fail, right? But anyway, technically means it means that for any bundle, and you can always find the epsilon ball, right? That Y is better than X, so that is what it means, okay? And why we care this assumption, okay? This assumption will give us indifference curve, right? Otherwise, we indifference set because, okay, this assumption actually rule out fake indifference curve, right? Because you cannot have a point give you a bundle. Okay. The thing that all the commodity that is same to this one must be a line, cannot be a set. Okay. Okay. Cannot be a fixed set. So that is the main thing, is when you try to draw indifference curve in your intermediate micro, you assume local non-satiation. It's not a big deal, okay? But it means that there's nothing that you would feel happy. Okay, always I give you something you're happy. Okay, I think it's not an issue for business school, right? I mean, because always money is in the function, and most of the time more money is better, right? At least you can donate anyway, right? So always you can there's no problem for business application in general. Okay, so we don't too much worry about this one. Now the next is called monotone, which is a stronger version of the local non-satiation. Here actually the bundle here we mean is everything is good, not bad. Okay, so everything is framed in terms of good instead of bad. Means that pollution, we don't model as commodity, we will model as absence of pollution. Okay, so instead of taking, we have one maybe we have one rubbish on the ground, we have a no negative absence of rubbish in the ground. Okay, much more clean. So that's a way in this kind of modeling, then you would imagine that the more the better, so they're goods. Okay, and the first one is called monotone. It's very simple, right? The first one is more cannot be worse. Okay, so we just try to draw a graph here. If you point X here, okay, more cannot be worse, right? Monotone means that the following: this upper set, okay, will be no worse than X. Okay, and of course we don't know what happened in all this, the purple. Okay, it depends on indifference curve how we draw it, right? But we know that all the orange are bad, right? No, cannot be better than this one, right? And there would be indifference curve here, right? So that is the monotone give us, right? In the northwest direction is better. In this southwest direction, there's a worse, and the other purple direction you don't really know. Okay, so that's monotone, and there will be one we actually usually use. It's called, we call strong monotone, which means including the horizontal line and vertical line that we can say, right? The horizontal red line is always better. Okay, and if strong monotone, the purple vertical horizontal line also worse off. Is that clear? And we always assume this guy almost, so that's not a big deal. We keep this because in the econ textbook they always do it this way. Okay? But very often we just directly assume strictly strong monotone, and we assume that will satisfy the local non-satiation. Okay, and is that okay? That would be the assumption. Okay, that's a good. That is something we always assume. Okay, so that means that this is something we often make the assumption there. Okay. Actually, we are making this assumption as well. Okay. So for marketing people, you do behavioral. That is something you may testing, right? So you will be testing this kind of stuff. Okay. Now so we have one assumption, local non-satiation. We have monotonicity, and now we have come up with the most challenging one. It's called continuity. Okay, continuity. Okay, there are three different kind of versions. Okay, I would say the first two are very technical, and they're equivalent. And this is the first two you'll find in the textbook. Okay, I think the first one is you can find it in the Masco-Lewis and Green. The second one you can find in Jathill and Rennie. The third one you can find in the Rubinstein textbook. I found the last one is most intuitive, so that's why I start from the last one first. Okay, the first is very simple. If we have strict preference, X is better than Y. Okay, so what I'm going to say is we can find radius Rx and Ry, means in the nearby X and Y, okay, we can still find things that keep the same relationship. Okay, what does that mean? If X better than Y, do it this way. Okay, maybe it's easier to draw a diagram. So suppose I have X here, I have Y here. Okay, and you tell me X is better than Y for sure. Okay, so what they're going to say is I can find something nearby X, which is called X prime, and I can also find something nearby the Y, sorry, a different color, call it blue color, call Y prime. Okay, this X prime is still strictly better than Y prime. So that is called continuity. It's very simple, right? Your strong preference still remain the same if you slightly change your bundle. Okay, you are not continuous because searching a little bit cannot be changed. That's continuity. Continuous means, right? It's not something like I change a little bit, then it's off. Right? So some people do have a non-discontinuous preference, right? I mean, I look at some marriage market website, and they have to say, the boy must be 180 meter, cannot be 1 cm less. 1 cm less, no. Okay, no matter how rich they are, have to be 1.8 米. Okay, 180. So that is a discontinuous, right? No matter how good, how handsome, how rich they are, is if the height is a 1 centimeter off, then gone. Okay, then it's not continuous, right? If you prefer a guy or a woman, whatever you think, I mean, I just make assumption, right? And you compare the two, if slightly change a little bit, you still remain the same. Yeah, they're continuous. If slightly off, then you're different, then no. Okay. And that means the strict preference continue to hold in nearby bundle. That. Okay. And if you're going to go to technical, which is said, which actually we use it, is what we said is the no worse set and no better set actually close. Okay. Which means that the boundary is there, right? Or in the case, what's called the convergence sequence, a limit in there, right? So it means that there's a sequence of X, sequence of Y, and Xi better than Yi, and the limit also continue to hold. That means the convergence thing. But I don't think the 1 and 2 will be very useful to remember. Okay, but actually there's a math thing, and this is the easiest to remember, and they're the same thing anyway. You know, in some time the proof you will see they actually directly use this too. They use very useful for the proof, but not very useful for remembering and the definition. So that's why I would take the Rubinstein idea, right? Your preference continuous means that no matter if you think strongly one better than the other, slightly change doesn't change. Do note that I only require the exist. Okay, it can be very big, very small, and as long as this whole. Okay. And I only need one bundle like this. I don't need all the bundle, right? So it's like I just find the nearby. There's exists something nearby that still hold. Okay, that one is usually strong, right? But sometimes we have very discontinuous, as I mentioned, right? Something that you are never able to compromise, right? Then that's the case. Okay, is there any question? So we have continuity. Okay, so as I mentioned, what is the famous thing that violates continuity is called lexicographic. Okay, so this is the one where often in our daily life we express this kind of preference. Okay, lexicographic preference is what we call what sometimes we call dictionary preference. Okay, and how dictionary, I mean English dictionary, related is you look at, probably you guys don't look at dictionary anymore, But anyway, in the old day dictionary is a book, right? Which words are ordered by the first letter and so on and so forth, right? Things are ordered by first letter first and second letter second, right? And that means that the same, you have a lexicographic preference means that you have a K preference relation and X better than Y if the first K they're the same, the last one is still better. Okay, that means that what you're going to do is you look at the first one first. If first one better, then you're done. Okay, so basically that's what happened in the Shanghai marriage market, right? First thing, house, yes or no? No, then gone. Second, Shanghai Kuko, yes or no? And then I don't know. You can check. I don't know what, because that is the example I often give. Shanghai marriage yeah, so can I see the thing? Yeah. Something like this, probably many of you might have know it. Yeah, when I visit Shanghai, I often go there to have a look, because this is one of the I don't know, one of the well-organized market there. I think just wait a second, because I think the Microsoft image search is not very good. Say, this one, I don't know, USA marriage and citizenship. So that is the lexicographic, right? Because that is the thing. And let's see what do we have. I don't have the picture, but right, you see this one, right? It's trying to say what kind of height is 1 meter 6, right? And 40 down, and look good, money, young, right? And the last one is they don't care about the Kuko, right? So that means that the guy, right? Of course, he is rather not too young, but anyway, this is the lexicographic, right? Because he has to satisfy the height, age, and so on and so forth, right? All the matter, right? You have to try to rank the way they write is actually F order, right? If same for all this, right? So that is the example that actually we do have a lexicographic, right? Actually, when you graduate, right, you have to pass the coursework, right? Finish all the paper and graduate, right? There's no way to compensate if you fail the exam, but there's no way to compensate. I mean, a lot of time it's like this, right? It's not something is less lexicographic in the way we make decision, right? For example, some people like when we buy the smartphone, always have to iPhone regardless of what, right? If you do iOS system, then already there, right? Compare all the phone there, iPhone, always iPhone. No iPhone, they may use Android, but iPhone there, the iPhone, no matter how other things look good, right? So we often actually behave like this, right? So it's not something very unnatural, right? So suppose we consider a marriage partner, usually we would restrict themselves to human being, right? Or opposite gender, right? Or so on and so forth, right? Usually we don't think about marrying a rock or marry a laptop, right? Or something else, but people do. I mean, outside in the US, right? Some people married to a mountain, some people married to a temple, right? That's a thing, but that is the stuff. Okay, and do note that why we want to mention this one is because when you have lesser graph preference, later we'll see there is no utility function. Okay, so that is the main thing why we don't mention this, because we often we're lessographic. Okay, and then we don't have the way to write the utility function. Okay, then how should we do it? Actually, do you know how do we do it? Anyone have any idea how do we do it? When people are lessographic, which actually we do when you're marketing, right? How do we do? We will assume there are different type of people, right? In the marketing, we assume people who are like iPhone will be follow some utility. People who like Android phone will have another utility. That's it. Then we're done. We will assume the different types of people, and we're done, right? Then under that sense, they will have preference like that. Okay, so that's a thing that usually we do a side cut to that one, because we don't have the way to present it. We don't have a single utility preference to represent this type of preference. Then what we're going to do is we decide two type of agent. One type is just by iPhone, the other type is by Android, right? And that is the way we handle, right? Of course, type is not very well defined in our class yet, but you know what it means. Okay. Next, or probably the last one, is called the convex preference. This is same as continuity. Is made for the sake of making optimization. Later you see, making the convex preference is to make your utility function quasi-concave. To make the concave is to ensure when you do maximization, you have a solution. Okay, of course, this need not hold, and you will have a multiple solution when you do demand, but this is the thing we assume in the standard thing. So what is convexity? Convex is very simple. It just simply means if you combine two things, okay, it is always better than the worst of the two. Let me repeat, okay? I give you two bundles, X and Y. By completeness, you're able to tell me X better than Y, Y better than X. Let's assume X better than Y, okay? And Y is the worst one, right? So you try to make some combination of the two bundles, X and Y. The combined one is better than the weaker one. So mixing thing is better, okay? A standard thing when you learn undergraduate, when we go is when you try to go to the, I don't know, many of you are CHK student, right? You go, the nearby canteen is called the Zhongji canteen, right? When you try to buy the sell way is the barbecue, the stuffs, right? You can order one stuff, cha xiao or xiao ji, then is I think it's $40, right? And I forgot the price. But if you buy two, right, it's more expensive. But two is not offer the same amount of meat as you buy one, because people love for variety, right? So the reason is when you have X maybe chicken and Y maybe the duck, and you combine some chicken and duck, is better than just worst of the two. Okay, that's the idea. Okay, so and you can see from the menu a lot of time mixing thing is better, right? At least better than the worst case. But sometimes, of course, mixing is bad, right? Suppose I give you, sometimes good. I mean, if you're from Hong Kong, then say suppose X is coffee and Y is tea, and probably you would think drinking coffee and tea is separately is better than mixing them, right? But of course, some people would know, if you're from Hong Kong, one of the very famous drink is called Yin Yang, which is combined tea and coffee. Some people like it, some people hate it. If you like it, it's a convex. If you hate it, then it's not convex. Very simple. And strictly convex means the combined the two is always better than the worst. Okay. So later you will see this one will lead to what we call quasi-concave preference. That is necessary for a unique solution for the maximization problem. Is that okay? Okay. So as I said, indifference curve is what you learn, and then I think now you know what assumption is behind when you draw those things. Okay. The main thing of this is a lot of math is trying to get the idea what is behind what we're doing. Give you the idea. Of course, we will never remember what we have done, but it'll give idea that you know where to find when you try to do things, right? Because when you do research, right, you're trying to do things that is not have been done before. So the easiest thing is go to foundation and see what can be changed, right? And actually, when we talk about transitive preference, right? I think after so many years, only the last 5 years people start to, in economics, try to work out when you would have when you have intransitive preference. Okay, and you can imagine there's a lot of things can be done if you try to vary something, and things can be different. Okay. Now, with preference, now we go back to your familiar utility thing. Okay. So the goal is, I remember, is we try to connect preference and utility, telling you what assumption you need to make on preference, really you what kind of assumption or property on the utility function. That's the goal. Is that clear? So, of course, we start with what's utility function. Utility function is nothing but just a numerical representation of your preference. Just give a number to a bundle, okay? So which means that the definition is actually a function, okay? From the consumption space to a number, okay? Which means that I have a consumption bundle, consumption base. Each bundle there, I give a number, okay? This bundle, number 1. This bundle, number 2. This bundle, number 3. And the number given has a meaning, has an order. The higher the number, the better. Okay, so that means that here, a preference represented by this function if, okay, note that this if is not if only if, okay, as long as I pick up things from the consumption space, x is better than y, as long as this number I assign is higher, no less than the other one, okay? If x better than y, x has higher number than y, okay? And why actually you want to ask why we want to do this, okay? The reason is we are not mathematician, so handling number is actually easier than handle the binary relation. And if you are hardcore people actually do the binary relation, okay? But that can't bring you too far, right? Because you cannot talk about derivatives and those kind of tools that we use. So that's why we actually try to make everything into numbers that we can optimize easily, right? So otherwise, we optimize a number is much easier, right? You learn calculus, you know that will be much easier to handle that thing. So that's the reason why we look at utility function. And as I mentioned, when you have lexicographic preference, later you will see we can't have this. Okay, so we have to find out some way to make your model work, right? Is to make some other way to make it work, right? Assume different type of agent instead of one type single agent. Okay. Now, the first thing is, sorry, go back to it, is the if here. Okay. If here means that it's not if and only if, right? If means that as long as this satisfies, it's true, right? So that means that there are many, many ways to assign, right? So you assign this way, I add 1 to that same representation, okay? So it's not a unique one, okay? The first one is not unique. So it means that the first thing is when you do a monotonic transformation, the same thing, okay? So here, the example will be like this, right? You have xn plus 2, you're just adding, okay? Here, actually, when you write this, the assumption here actually will mention, to you, this is called perfect substitute, right? You increase 1 by 1, reduce 2 by 1, the same. So they're the same thing to you. And this representation is same as this representation, okay? So this is very natural. And probably you will ask why I want to mention this thing, right? It's because when you're given a utility function that is very crazy, okay? you can always transform in the way that you like it. And you can still do it. Okay? So that means that when you run regression, it doesn't really matter, right? You can do any log transformation, you can do whatever transformation, it's still fine. So that is the one thing that actually imply in your empirical work, right? You take function, you can write whatever way you like, it's fine, as long as you keep the order. Okay? So very simple, but the idea. I'm not going to prove, I think it's very simple. Everyone is able to handle it. If any question, then ask me, okay? It's just like any increasing function, the thing is still the same, okay? The proof is trivial. I'm not going to go over it, okay? Now, as I hint earlier, there would be a proof that trying to show you that what assumption you need to, you can use utility function. The very basic one is we call continuous, okay? And monotonicity is not needed, but I just put it here because make our proof easier. Because I'm trying to present the proof, the only proof for this class, okay? And I will do the proof very quickly, okay? Not going to detail. If you get it, don't get it, it's fine. Because it's very graphical, okay? So how we prove this one is by construction, okay? The formal proof is here, but I don't like the formal proof, so I skip, I do the graph. So the proof will be the same. Look at this graph, you get everything, okay? So make our life easier, we start with two-dimensional, but you will see multiple dimension is the same thing, okay? So look, ourselves, we start with the bundle X, this guy X, okay? So what we are trying to do is utility function, right? By construction means for X, I try to give a number to this bundle, okay? I'll give this number in a consistent manner first, okay? The first thing is, what at the left side do is, I give number to every bundle. The second step is trying to show you it actually represent the preference. Means that the higher the number, I prefer that bundle more. Okay, let me repeat the statement. That's a very important step. The first step is I try to, by construction, every bundle, I give a number. First step. The second step is the higher the number, the higher preference I have. Okay, how do I do the construction? I start with any arbitrary bundle called X, okay? And by monotonicity, okay, strong monotonicity, A is better than X, strictly better, right? A has more than X, right? In the horizontal, vertical dimension, right? X is A better than X. The second thing is B is worse than X, right? Because B has less on the horizontal one. So X must be between A and B, right? You agree, right? The second thing is, remember, we have monotonicity, right? So we have indifference curve. It's not fake, okay? So that means that I would able to come up with a indifference curve is a downward sloping, right? No matter how downward, it's just like downward, right? Cannot be upward, right? Downward sloping. And the downward sloping line must cut through the 45-degree line, the dash line in somewhere. Okay, this is a 45-degree line. 45-degree line, right? That means the E is just 1, 1, right? So vector 1, 1. Alpha, because the coordinate will be the same, right? Alpha is a single number. Okay, let me repeat. What I'm doing in this is by construction, every bundle, I can draw a indifference curve, and where it cuts is the number I assign. Is that okay? Is that clear what I'm doing? Is that okay? Anyone have question? Because you have question? Because it's a small class, let me just ask. Because this only proof I'm doing this today, okay? No other proof. I mean, if you don't really get it, doesn't matter. But just trying to make sure that, you understand, okay? Let me repeat it. Just what I do is I draw the indifference curve, right? Because this coordinate is 1, 1, right? So I can use single number to represent this, right? For every bundle, I map into the horizontal, the diagonal, and diagonal can be represented by number, okay? Now, second is what I'm going to do is trying to prove that is true. Okay, it's actually the higher the number, the better. Okay, so let's consider the case by construction. I'll consider two bundles, X and Y. Okay, and by construction, I'm able to find a bundle in the diagonal which is indifferent to this, right? And same for Y. Okay, and because this is same as this is same as this, by transitivity, then this one is true, right? And you can take away the E, right? And because this is higher, this number is higher. Okay, so this is by construction. Okay, of course, if you want more elaborate argument, it's actually there. It's actually in the proof before. Okay, that is only there. Okay, so that is you get the higher the number, right? It's better. Okay, it's by construction. Okay, doesn't really matter if you remember the proof, because indeed there are more than 10 ways to prove this. Okay, this proof I adopt from the Jetil and Rennie. You can read the textbook if you miss something. Okay, and the proof will not be important to give you. This is trying to give the taste of what kind of proof we are doing in the textbook. But of course, you can skip it. Okay, if you don't really useful, because there are more proof than your time you can read it, right? So you can't read everything, right? Because remember, the problem is choice, right? You have to make decision what to read, what not to read. Okay, so that is the idea. So the proof is here. Not going to go about it. Okay, and the next two thing is whether this is continuous. Okay, and actually, indeed, it implies continuous preference. Okay, I'm not going to prove it because even in Mascolo, Winston Green, the textbook, they put in technical, right? Even for that book. And that one is more difficult to understand. If you look at Jetil and Rennie, the proof is more simple. It involves only 4 or 5 lines, but the argument is more technical, so I'm not going to do it. Okay, if you want to know, you're going to check it out. So I just skip. Okay, and the next thing is because we often use differentiable preference. The question is, what kind of utility? So what kind of assumption on preference that gives you a differentiable continuous utility? The answer is we don't solve it. We just use it. And if you read the book from Rubinstein, the lecture notes, they will give you what assumption on preference give you this one. Okay, and usually the differentiability and will be a technical thing. People will not complain that one, because the reason is because any monotonic transformation is still fine, right? So that's why for differentiability, usually will not complain for that one. Continuity may be difficult to take, right? But if you assume continuous and differentiability is, if you learn math, right, there's difference, but the difference is not huge, right? So usually you don't really worry about that much. So continuous will be fine. Okay. And because continuous actually is an issue of less rapid preference. For differentiability, usually you don't have a good example to say my preference is continuous but not differentiable and I have a problem. No. But my preference is not continuous to have a problem. And we do have example that we have a discontinuous preference. But non-differentiability, no, I don't think any real world issue actually with that. It's really purely technical. Is that okay? But maybe I'm wrong, but maybe you can write a paper on differentiability. But I can't see this is right here that yet, but maybe you are better than I do, right? Now the thing is, as I said, I try to connect the preference to utility, so that's the thing. Okay. I guess we have many definitions of concave utility. Okay, and later you will see the concave utility is driven by the convex preference. Remember, the convex preference is combining stuff is better. Okay, and that will lead to a concave utility. And concave utility, if you remember from the math class, is required for maximization problem. Okay, and in economics, they would have bunch of concavity. Okay, but what we actually need is usually what we do is just assume this directly. We actually assume the strict concavity. Okay, strict. What does that mean? It means that combining stuff is better than separate them linearly. Okay, that's what we are saying. Lambda is still the same. Lambda. Sorry. It's you're right. I should don't have the. Oh, it's open. Yeah, open. Sorry. Yeah, it's open. Thank you. So very good catch. This one should not have this guy. My mistake. Sorry. And this strict concavity is usually directly assumed. Okay. And of course, there will be weaker version of those. Probably ask why we have to use this weaker version. It's because in order to achieve the optimization problem you have solution, you only need to use the weakest one, which is quasi-concave. Okay, and that's the reason why economics is very care about this when you learn from econ. But since we're B school, so just start with we just have this one. Okay, this will imply the weaker version. Weak version means the combination is better than the minimum of the two. Okay, so you can see this one, right? It's exactly the same idea as we have the when we mentioned about the a convex preference, right? If x better than y, this is the thing, right? And later, actually, you can be shown this equivalent, right? When you have convex preference, it's same as the quasi-concavity, okay? And but when you do proof a lot of assumption application, we just directly assume this guy. Okay, that is the thing we have. Is there any question? I'm not going into any details or all the definition because you don't care, and I don't care, right? We just assume this one. What to mention is the first one is equivalent to the convex preference, and often we work directly because of convenient math. We just work on this guy, okay, and that's what we need. Okay, is that okay? We work with the stronger version because the stronger version is easier to handle. Later, you will see example because we have this, right? Your indifference curve is like this. So this is the thing we need. Okay. So as I said, why we have to introduce quasi-concave is because this is proof. I'm not going to prove it. It's the result is when you have quasi-concave, that it means you will imply your preference is a convex. Okay. So of course, when you actually do your work, you assume strictly quasi-concave, then actually you have assumed much stronger than convex, right? But that would be no problem. Okay. You just assume we have combining things is better. That's the thing you remember. Okay. That is the thing we usually assume when we make this, when we write our consumer. Love for variety. Combining, I give you 2 iPhones, okay, or 2 Androids, okay. Regardless you like which much, if I give you 1 Android, 1 iPhone, it's better than the worst of the 2 cases. Okay, that means that there are no complementarity, right? Probably you would rather have 2 iPhones and 2 Androids, right? Because they can talk to each other, right? If I give you 1 iPhone and 1 Android, probably doesn't work as well, right? But anyway, this is the thing we assume. Okay, I'm not going into the details of this unless you want me to go over it. Let's skip that part because I put the gray thing. It's just you can be skipped. Okay, I just put there in case you want to look at. But I don't see the reason why. I mean, unless you really want to go into that, okay, because it's too fundamental Okay. Now, here is I want to present two useful results that can be useful for your model. Is the first thing is quasi-concavity, okay, will be preserved when you do monotonic transformation. Okay, that means that when you do optimization problem, it's not an issue. So you can freely do monotonic transformation. The solution is still a unique one, not a problem, right? And the second one, how can you check, how can you make sure that it is a quasi-concave, right? You can see if I have a monotonic function, I impose on you, okay, this guy is concave, then this one is still it's a quasi-concave. This is how you check usually, okay? You do some monotonic transformation, it's a concave, then you're done, okay? So maybe you square it, you take a log or whatever, usually take log, right? It's still a thing, then you're done. Okay, that's how you check usually, because checking quasi-concavity is a pain. But of course, you just assume usually, but sometimes when you need to check, that is the way to do. Okay. This only serve for sometime you go back, you need this property, then you do it. Okay. So now we reach the goal, try to connect ourselves from the preference to utility. Okay. First is if our preference is monotone, our utility is also monotone. Okay. Monotonicity preference transfer to monotonicity of utility. And as I said, if your convex preference can convert to your quasi-concave utility function. Okay. So these are the assumptions that we often write, and this assumption we have. Okay. So hopefully I give you already the preference. Oh, sorry, I didn't notice I have a break. Okay. Yeah, maybe I have a break. Sorry, I didn't notice. So let's have a break of 15 minutes. Hi. So, half an hour left. So hopefully we can cover as much as we want. I hope to be fine. So, one thing that we often talk in the apply is called the marginal way of substitution, right? You learn from the undergrad, right? Basically the slope of indifference curve, right? And that means that if you MRS IJ means you give up 1 unit of I, how many J you need to compensate make it better, right? And actually it implies actually somewhat of monotonicity, right? Otherwise you cannot, you'll be not negative, right? Not substitution, right? And it's called the slope indifference curve. I think you learned it in your math camp and your intermediate. So I'm not going to go to detail on this one. Why we wanted this is when we talk about the optimization problem, we will come back to the MRS again, and turn out to be if the consumer price taker, right? The MRS will be same as the price ratio. Later we'll talk about that. But this you learn in undergrad, but just to say it again. Okay. So one of the first thing is usually we have 4 special type of function that we use for our apply work. Okay. Basically, this is the thing that you work, right? The first one is assume perfect substitute, right? Adding is very normal, right? That's it. You add things, right? So that is the one substitute, right? You increase x1 by 1 and you reduce x2 by 1, it's the same, right? This is standard. Alpha is just different rate of substitution, right? So alpha in this one, the MRS is 1, right? And in general case, the MRS determined by the alphas, right? So that is very simple. And the other one is also very common. It's called the complement. We use it is not because of it's realistic, because the math is simple, right? The linear is also simple. The perfect complement is very simple as well, right? And sometimes it's also realistic, right? Because suppose you have a smartphone, iPhone, and you have a, I don't know, you have you need to buy a, I don't know, the earplug, right? The Apple AirPod, yeah. Then you need one iPhone, you need one AirPod, right? Something like that. Or the iPad, you have an Apple Pencil, okay? Apple Pencil, right? I mean that would be you need pair, right? And that is the idea, right? The traditional thing is like the left shoe, right shoe, so on and so forth. But that would be, as I said, this is a very good way. You see a lot of models that assume this to make your calculation easier. Okay, so and we actually do it in modern paper as well, not just in classical textbook example. We actually derive the model. This make you easier, right? And do note that the marginal substitution for this one is not well defined. Okay, at the king is not well defined, but other places is defined, but it's very weird anyway. You don't talk about the MRS in this context anyway. And the other one, I think is usually you would see is called the Cobb-Douglas, right? That, I mean, the genetic form is called the CES, but this one will be the thing that usually you would do when you do a normal thing, right? So probably you would do the 3 thing is like you do the perfect substitute and perfect complement. And when things work out, you do the Cobb-Douglas, right? So this is usually the 3 things you work on to make sure your model will fly. Okay. My share screen yet, right? So now I think we have everything there. So we just go back to the classical things you have learned in the intermediate. So I try to be fast here. I just want to highlight the main thing there. If I'm too fast, slow me down. But I think most of you might have learned it. Okay. If you think I'm going too fast, tell me. Okay. Because as I said, everything is choice, right? If we spend too much time here, then we have less time on other topics. Okay. So starting from this point, we are thinking the price is exogenous, okay? And it would happen to be good for consumer, right? But only if the consumer is small, right? The consumer like Walmart, when they try to buy stuff, they're very strong. So rather than he is a consumer, but he's all the supplier become the other way around. So it depends on who they are. But in the first half of the class, we assume everyone is non-strategic, right? So the price is taken as given. Okay. So in the other word, we take an environment as given. He's not going to change the environment. So in this case, the environment is the price. Okay. The price is exogenous. And in the chapter 3, we talk about equilibrium, where the price will be determined endogenously, right? Either you assume the entrance of firm to make sure the price equal, demand supply equal, right? And so on and so forth. But we assume price is exogenous and positive. One of the reasons that we assume positive price is to rule out of corner solution, make our life easier. If price is 0, there's some issue here, okay? And price is 0, you'll be inconsistent with usually what we call strong monotone, right? If something that is free, you can consume better more, then you would keep consuming. There's no solution, okay? So that's why we assume the price is positive numbers, okay? It's not 0, okay? If 0, that's called a free good. In economics, there's something that is called free, right? It's oxygen. Is to some extent you don't need anymore, right? So so that's why there's something. But for economics, for business application, I don't think it's an issue for us because we focus on things that is not free, right? And of course, some of you may argue that a lot of freemium product, right? And but the thing is, usually in that case, you would not consume a continuous quantity, right? The IT product are free, but you only consume 1 unit, right? I give you WhatsApp is free, you only use 1 WhatsApp, right? How many accounts you need, right? Even you have minimum account, the same thing. So consuming more would not make you monotone, right? In that, because free, in that case, it's not monotone, right? There's a maximum you can do. So in that case, that's fine. But I hope it's clear why you make those assumptions and when they're valid. Okay. And the next one is budget set. Here we make our life easier. We just make the budget is a downward sloping because it's a perfect market there. Okay. You can buy as many as you want at the market if you pay the price. Okay. There's no other restriction whether you can buy it or not, right? In some cases, right, as I mentioned, right, company will do bundling, right? So you cannot buy any quantity you want, right? But of course, in economics, they will try to argue, oh, we're talking about not a short period of time. We're talking about long run horizon. In that case, continuity is not an issue, okay? But anyway, for business application, probably that might be an issue, right? Because you're restricting the consumer in some period of time. Then you can make sure that they would not have this kind of budget set because force them to buy or not buy, right? But anyway, this is standard, okay? The budget set is just how much you consume less than your endowment money Y, okay? In this model, we assume the price and the budget Y is exogenous, okay? In general equilibrium, in the topic 3 we study, we will endogenize those, okay? So it's exogenous, okay? So this is the most important problem we want to learn today. It's called the utility maximization problem, which essentially said is you're given a utility function. Remember that is given from a preference, okay? And we have to arrive this utility function, we have to assume preference are continuous and monotone and so on and so forth, right? And you're choosing a bundle inside this set, okay? And make sure that you've satisfied the budget constraint, okay? And the budget constraint is weak inequality, right? But remember, when we assume, as usual, we have strong monotone preference. More of anything is better than you consume everything. So this becomes equality. So it becomes a maximization problem, choosing a number, right, in a set. and satisfy the constraint. So it's simple Lagrangian solution, right? If you want it to be more constraint, more inequality, then you will conductor. Okay. And if you learn principal agent problem or those kind of model or mechanism design problem, is actually a conductor or more advanced version of conductor, right? It's a bunch of inequality there, right? If you learn, there will be a lot of incentive constraint and so on and so forth. But if you learn how to do optimization, you can go very far in economics. But here we just focus on the simple one. Okay. But you can easily imagine you get some constraint. If you're firm, right, you're trying to maximize your profit, which we'll talk about later, right? If you're monopoly, then you may try to manipulate, right? Say you cannot consume X1 more than certain quantity to make sure that to maximize your profit, right? And so on and so forth. So there are ways that you can complicate this problem. Of course, the solution existence will be an issue, but in this simple model, things are very trivial. Okay. So the first thing is very simple. The first thing is to ensure our solution exists, right? Otherwise, what we're doing. So if you have, we just use the standard thing. If you have continuous utility and what we have the budget set is closed and bounded, there will be always a maximum. This is standard, your calculus theorem will tell you, okay? And usually we're on continuous function, right? There's no problem. Your budget is also set. No matter how you do inequality, usually it's also a compact. So that's this theorem usually always apply. So you don't need to worry about that. I think the more important is you want to make sure this is unique, right? Because and to ensure unique is very simple. As I said, if you have a quasi-concave preference, okay? And do remember, if you have quasi-concave preference, it means that, just draw a picture, it will be easy to understand. X1, X2. A quasi-concave preference means your upper set, the better set, is a strictly convex set, right? So the indifference curve will be looks like this kind of style, okay? Or no matter what style, it's like this, right? You cannot have a wiggling like this, right? Because it's not convex, right? So you must be look like this shape, right? And your budget is like this, right? So you can always find a solution, right? Because this, you always have this guy, right? And your budget is fixed like this, right? And you keep drawing indifference curve, and it must have a unique point. Why? If you have 2 points there, then middle is better. So it must be unique. So that's the idea. So why we have this, the strictly quasi-concave is assume. I hope I answer some of the question. Is there any question? So I guess you learned it in your math camp. Okay. The next one is Wawa's law. Probably you also learned it in your intermediate class. It's very simple. It just Wawa's law actually means a lot of stuff, but in this context means that you consume all your budget, so there's no money left on the table. So it means that when you have a strong monotone preference, which means strong monotone utility, then you will consume everything, right? Because if not, then you would just use all the money. So there's nothing deep here, but just because you read the textbook, they always prove all those kind of stuff. Okay. The reason why this is, I said, if you this whole, you don't need conductor, right? Otherwise, your life will be miserable, right? Solving conductor will be much more difficult. But now you can have Lagrangian, then life is easier. Okay. And as I said, if you have the constraint is complicated, then they have to solve Lagrangian. They have to solve conductor. Okay. So this is the thing that we'll be working. Okay. It's called looking at the FOC condition. And some of you is very good at math and you easily solve the problem, right? And you can solve the problem, but when you write a paper, usually people don't care about your proof, right? Care about your result. And once you write the FOC, then write it out, then probably people would ask you to interpret your result. That's important. And usually that's not taught in the class, but I think it's important. You have to know how to interpret your result when you derive your result, right? You can easily write a form. When you can easily write your result in proposition, right? I think many of you with good at math, there's no problem solving the model. But the important part is how you interpret the model. It's a B school, right? You have to know how to talk about your result. And we can prove it, but we'll do it later. The main result here is, as I have hinted, you will have your MRS equal to a price ratio. Okay, that is the result. And probably you would ask the reason why, which you should write in your paper, right? Because when you write equilibrium model at the end, right, when you the marketing or finance or whatever, right, at the end, right, finance, everyone probably know, right, the end result, the main pricing equation, right, is no arbitrage, right, or the price kernel, so on and so forth, right, and the same thing here. Okay, what you're going to do is the price ratio, PI or PJ, is the exchange rate between I and J in the outside market, right? You can always exchange I and J according to this price ratio, right? Because you give up 1 unit of I, how much money you get is PI, and you can exchange for 1 over PJ of the unit of, right? Then repeat, right? This is, if you give up 1 unit of I, you get PJ money, and you can buy 1 over PJ, how many units you can buy from unit J, right? And the left-hand side is your internal exchange ratio to U. If you exchange I for J, this is how much you want to do, right? At the harmony of your internal mind, right? It must be the same. If not, then you can take 1 out and take 1 in, right? So that is the meaning, right? So it's the internal trade-off and the external trade-off, the same, equalized. There's no disharmony. There's no conflict between your mind and the market. Okay. So actually that hint why when the market is competitive, right? So the financial market actually tell us how people think about the future, right? Because every people trade, every people interact, there's aggregation of information on every people, right? Because if you think the market doesn't represent the future, you can trade, right? If market is competitive, right? Then everything is reflected in the real world. Right? So market is a price discovery tool, right? But anyway, this is beyond what we're saying. Okay, so as I said, you can infer preference on market price. That's exactly why we want to look at the price is sufficient to learn how people think about the future, right? So same, not just the price, right? The gambling, right? The horse racing, everything is reflecting people, how we think, so on and so forth, right? So if you look at, say, soccer, what the best way to predict soccer, who is going to win, look at the gamble market, right? If people think this team is likely to win, then they have the odd ratio, right? We follow accordingly, right? So, or look at, is it the inflation or the stock price? The economy going to go good or not, right? Look at the stock market, right? That's how you, that's what it means, right? And if you have differentiable and cosine-concave, right? What you have is, do I have the graph here? Right? Is the indifference curve, right? With tangent to this at the optimal. Okay, but anyway. So this is what I have said already. Okay. And this is the one that to operationalize this, right? This is the one you would write your problem in Lagrangian, take the FOC, right? And then this will be your solution, right? Usually there's no closed form, but if you make some assumption that a closed form, right? And you just do the division, you get the FOC, right? That's how you get it. Okay. And this is the Bravas law, right? Now, and this is another interpretation you often see in the textbook, and this will be useful as well. So you just swap it, okay? And probably people ask you the Lagrangian multiplier, the lambda, what's the thing? Because if you remember the optimization problem, there's a two-part, right? One is the optimal solution and also the Lagrangian multiplier. And the Lagrangian multiplier, we often in the empirical part is actually important. The theory is not very important as well, but in the empirical is very important because this is something that very useful, because in this context, the lambda from M.Phil theorem is the marginality of wealth. What does that mean? Because if you try to rewrite this cross multiplication, this is just the MRS equal to price ratio, right? And from M.Phil theorem is equal to lambda, right? And equal to du dy, a change of how much happiness you will have. Yeah, will give you one more unit of wealth. Okay, and when optimal, right, give one more unit of wealth is same as I give you $1 more. You buy this much quantity of I, and this gives you much happiness when you have one more unit of I. Okay, so that is why we call marginality wealth, and this is important in empirics because sometimes you often measure that one. Okay, and this is coming, how you measure this guy is coming from change utility over the price. Okay, and of course you ask how can we measure utility from the data? Of course, you estimate it from the regression, right? Assume the certain type of utility function, you want the regression, estimate this U and so on and so forth. You can calculate the lambda, right? This is how you discover the lambda. Of course, there's a lot of econometrics there, but I'm not teaching econometrics, so ask the econometric teacher for that. And of course, how to estimate this still remain a very important research question if you have large system of equations. But anyway, and I just want to mention a very little bit about corner solution, which we will never touch again. In this class, we always assume interior solution. I just mentioned here once is what happened when we have corner solution, okay? And actually, we don't require our math, right? If you know math, then you can use conductor, then you know why you have this one. Okay, you can derive the outcome. But we try to argue it from the sense of economics. Ask ourselves why we want to consume zero on a bundle. It means that even consuming a little bit is not worth the money, right? So is you take the P down, right? Then is spending on this give you less utility than other things you're consuming, right? So that is the meaning. And of course, you can see this is important for econometrics, right? Because when you observe some people consume nothing on that, then you can conclude this one. Give you some upper bound or lower bound, right? On the utility or the utility of wealth, right? So this is also useful for empirical explanation, okay? So, and the next thing is also very important as well is, probably you know as well, is we often do FOC and with the N, right? But you have to make sure that the SOC also satisfy, especially when you are using your own utility function, okay? Standard one is not an issue, but the non-standard one, you have to make sure it's true. And usually you have to prove all this crazy thing, okay? But this one is simple. In our model, we just assume continuous quasi-concave and differentiable. You can prove it's optimal. The proof is not difficult. Look at the textbook, the Jahil-Rani. It just spanned over 2 pages, but it's very elementary argument. I'm not going to talk about that here, but you can imagine that the utility function like this, right? And the solution is here, and the slope, the tangency requirement, then is the right solution, right? Let me repeat what I'm saying here. It just basically this one say, right? If this satisfy this, when the indifference curve, right, and the slope are equal, this is exactly the solution. That's what they say, right? Is that clear? Is that clear what I'm saying? But I don't think you have issue because we have solving this so many times. We just assume this is true, but we have some assumption here. Okay. Now, sorry, a little bit quick, but here is we now have a Marshallian demand, okay, function because of we have so many assumptions here. Because we have a, give me the price vector, give me your endowment and your preference, which is satisfy all those assumptions. We have a demand function, which means that give me price and the endowment. This is the unit I want. Okay. So that's a thing. So to arrive this Marshallian demand, actually there's a lot of assumption here. And the second thing we assume is the Marshallian demand will be downward sloping, right? This, when we run the regression, that's one assume, right? The higher the price, the less demand you have, right? So again, turn out to be, unfortunately, there's a lot of assumption behind to make it true. Okay, so let's look at that. Marshallian demand, we have several property. Okay, the first property is a little bit funny, but probably everyone would call it, we call no money illusion, which means that when you double the price, double the income the same. So usually people would refer to, sometimes we call scale invariance, or sometimes we call that independent of accounting unit, right? Whether you count in thousands or billion or million or US dollar, Hong Kong dollar, whatever, the same. Okay, and of course, I think people do not actually would be sensitive to those, right? And if you anyway, I just let it go. I mean, because I don't have time to cover. So the next thing is for Marshallian demand is most complicated in the sense that we don't know when one price change, say for P1 change, how it affect X1 up to Xn. Okay, of course we want P1 goes up, X1 goes down, something we want, but not always the case, right? And same if P1 goes down, how does it affect P2 to X2 to Xn? It's not clear. Okay, so since it's not clear, so that's why how economists solve the problem is to give different names, right? Suppose if your income goes up, Y goes up, your consumption for bundle, the commodity I goes up, that commodity is called the normal good. If you go down, it's called inferior good. So that is the meaning. The slide up later. Okay. So, and what about, as I said, if your price goes up, your demand goes down, then it's called ordinary, right? Otherwise, it's a given, but I don't see, but there's nothing exists in the empirical to show this is true. So this is fine. Okay. I think the most important part is besides normal inferior is comparative substitute, right? Is if the price of one good goes up, okay, how it affect the demand for the other one. Okay. And probably you would ask why we care about this, right? This economic stuff, right? And for business, we would care about how the elasticity, right? So you can see probably recently, right? You can see Tesla, right? They lower the price of their car a lot, right? Why they're doing that, right? And what they're doing, right? I think they're thinking a compliment because they charge. One of the competitive advantage of Tesla is there's self-drive. I mean the FSD, right? The self-driving stuff, right? By charging lower price, they boost the sales for the self-driving thing, right? It's a compliment, right? So I guess they just cut the normal car price and try to boost over this because other companies do not have a good automated AI system to drive compared to them. So that's one of the reasons why you can see that, right? And if you believe the electric car is a normal good rather inferior, right? That's the thing that's in their mind, right? So, but of course, that's an empirical problem. So I guess I don't have time. I think we cover half of it. So I think we should still able to be on schedule. So I'll see you next week. Okay. I stay behind to answer any question, but I can stay only 5 more minutes. Otherwise, outside, otherwise someone come and kick us out.